Well, good morning, everyone. I'm Julie Robinson. I'm the ISS program scientist, and a simple way to explain my function to you is that I make sure that throughout all of the processes and things that are carried out by predominantly engineers and operations specialists in the space station program, that there's a scientist there who understands the kind of things you're trying to do and is serving as your advocate, as your bridge, as your explainer, and maybe even as your ombudsman. And so that function has a variety of extensions into all the different levels, from selection through payload development, through operations on ISS, and even to the results afterwards. I have people in my office that, once you've done an experiment on the space station, are going to keep calling you for the next 10 years to find out if all of your publications are out yet. And that's really important for the overall space station, to make sure that someday when the space station is ended, we have a complete record of those accomplishments. And I believe very strongly that the many accomplishments of space station, and some of those that will be on everybody's tongue for the next 50 years, are those things yet to come, and they may be an idea in the head of someone in this room today. And so we're committed to making sure that those great ideas find their way to the space station. On the side of microgravity science, of course, if you think about it, every experiment we've done here on Earth is uncontrolled because we can't control gravity in those experiments. And you'll be hearing this morning a wide variety of disciplines talking about precisely that. What does the lack of gravity mean for those systems? And so as you think about that, think about the experiments that you're doing in your laboratory, and is there something that might be different if you did that experiment in space? And that's where true innovation comes, as we move to different environments and can do experiments that we couldn't do any other way. For the next few minutes this morning, I'm going to talk to you a little bit about the facilities on the International Space Station, just to give you an overview of the amazingly capable laboratory that's available to you. I was just at a scientific meeting, 6 or 8 months ago, and somebody went up to the microphone and said, you know, what we really need on space station are some freezers. And I had to horn my way up to the microphone as well, and I said, well, you know, we've had freezers on space station for many, many years, so that one has been taken care of. And in fact, that's true. There are a number of facilities that are exactly the facilities you might need in a laboratory on Earth that are available on the space station. There are, of course, a number of things that are challenging for working on a platform like the space station, so you might want to think of it more as a field laboratory or field camp. In fact, we look at Antarctic research stations as a model or as a comparison or benchmark for the things that we're doing in the space station. Some of you here may be in the Earth and space sciences, and you don't care about the microgravity environment or even the pressurized facilities. What you really care about is the stability of a platform and how it might compare to a free-flying satellite that you might use to mount an instrument. And so I have in my presentation today a large number of detailed charts, and they're there not for me to talk about with all of you today, but to serve as a reference for you as an entry into understanding this platform and its capabilities. So if I could have the next chart, please. My presentation is divided into 4 segments. I have a few overall facts about the space station, a little bit about the internal accommodations and facilities, a little bit about the external accommodations, and finally the question everybody asks is transportation. How do you actually get there? Next chart. So just a couple of facts about the space station. If there are people here who maybe worked on space station very early in its time frame, it was much smaller back then. It's really changed dramatically over the last 2 to 3 years. It's now the length of a football field end to end, including the end zones, and inside it's about the volume of a 4-bedroom house. So this is a capable laboratory. It's got 6 resident crew members available to work experiments day by day. Next chart. And it's an international endeavor, meaning that there are certain modules that were provided by partners, such as Japan and the European partners that comprise the European Space Agency, as well as Russia. We also have wonderful working groups with those partners to trade access to hardware when that's needed for our scientists. And we had worked together even in the design and development of the research facilities so that they wouldn't be overlapping, but instead would be complementary. Next chart. Now this is a quick chart on the microgravity vibrational environment, and you'll hear in a talk this afternoon why you might want to care about that. I think Brian Modal will be talking a little bit about microgravity environments in slightly more technical detail. What this shows you in that black line is the requirement, what we sought from a microgravity perspective. So, you know, the space station is free falling around the world in orbit, and vibrations are the one thing that you have that disrupts that nearly zero gravity vector. And so if you're doing an experiment that's very sensitive to tiny bits of gravity, micro bits of gravity, then the vibrational environment could be really important to you. And so what these charts show you is in different parts, using our SAMS measurement system, how close we approach that. And then you can see in that blue line, if you put it in an ARIS rack, a vibration isolated rack, how low the gravity actually becomes at 10 to the minus 1 micro-G. Next chart. Now there are a number of on-orbit resources provided to payloads, things like power, data, internal rack real estate, and crew time. Next chart. There are also, and this chart's a little bit technical, but the key to point out here is there are upgrades in work, in particular in the data and communication system. We knew when space station was designed and built that communications and data infrastructure computers were going to make massive advances during the time of construction, and so it's an upgradable system. And those capabilities are continuing to be enhanced. For example, we'll be having an external wireless high-rate data on orbit and so forth that make it much easier to implement experiments. Next chart. This chart gives you just a sense of how the research rack facilities divide out by partner. All the orange are racks that are installed on the space station. You can think of a rack, it's about the size of a large refrigerator. It's a modular unit, and it represents a lab bench. Of course, one great thing about the space station is you can have a lab bench in front of you, one overhead, one behind you, and one at your feet. And so you can work in all 3 dimensions. But they're essentially lab benches. And we cluster experiments on those racks that, or cluster hardware on those racks that might be used together. We also cluster racks together that might be used together. So for example, in the Columbus module, Europe has their physiology facilities, and we have our human research facilities there as well. And that way you can share hardware between those systems. Next chart. This is just a sort of Facebook page for all of the different rack facilities that we have on orbit. We have the 2 human research rack facilities, which are primarily physiology equipment, but they also include things like a refrigerated centrifuge that's useful in any laboratory. Our microgravity science glove box, the express racks, which are multi-user, modular, changeable facilities, some of the specialized racks for the physical sciences, and the specialized rack in the window facility. And I have a little bit more detailed charts on these, which I'll go through quite quickly. Next. And we'll skip this page. This is just some facts for your reference. So as I mentioned, the express racks are our multi-user interfaces. It's not that difficult to build to the standard interfaces in these racks and use one or more express rack inserts to do a specialized experiment. Here you see a picture of Thomas Reiter working with our EMCS, which is a centrifuge facility that can culture small animals and small plants and do it at variable gravity from 0 to 2G, which lets you do all kinds of controlled experiments with its 2 centrifuges. And at this time, the NASA program, what Rod Jones showed you on the right-hand side of the screen, uses about 50% of this express rack real estate. So it's a great resource for future payload development. Next chart. And this is just a more detailed fact sheet on the express rack. Next chart. And let's skip one more. Well, glove boxes are a really important component of any on-orbit laboratory because anything you would use on a lab bench, of course, will float. And so you can't use a beaker and keep your experiment in that beaker. You've got to have it in contained environments, and the glove boxes are one of the ways that we do that. Next chart. Freezers and refrigerators are another important component. We actually have 3 Melfi freezers on orbit. This is a picture of one of those. And those can go as low as minus 80 degrees. So in the same way, those of you that are in the life sciences, the first purchase you made when you set up your first laboratory was a nice freezer, and it's basically the same thing that we've done on space station. This allows samples to be held frozen until they can be returned to Earth. And then we have smaller freezers and also cold bag cooler systems that are used to return these samples and transport them back and forth. Next chart. And this gives you a rundown of the Merlins, which are both incubators and refrigerators and freezers to minus 20. The Glaciers are freezers that can go ultra cold, as low as minus 160. and then the single and double cold bags with ice packs, which are basically our high-tech patented cooler systems with phase change materials. Next chart. Of course, you may need to keep things warm for the life scientists, and we also have a number of different incubators, culture systems, and centrifuges. Those incubators that are on orbit will likely be augmented with some additional incubators and culture systems that are pre-decisional at this point. But there's definitely an emphasis in having the infrastructure on the space station support the broadest range of biotechnology and life science experiments. Next chart. And let's skip off of this one. For those of you interested in space and earth sciences that are here today, of course, many times you want to be outside of a shirt sleeve environment, and many of you may be looking at what kinds of instruments you might mount on the external locations on the space station. But it is useful to know if you want to test a system and test something very equivalent to what you would test in an airborne platform, that can be flown to the space station and operated in a shirt sleeve environment without any particular space hardening for testing. And that would be mounted in the wharf rack, which is shown here, which is over our optical quality window in the US laboratory. And so that optical quality or telescope quality glass lets you, when you remove the scratch pane with all the right safeguards in place, lets you test that instrument with a pretty broad range of transmittance through the window. So that's a really great option for doing some preliminary testing. Next chart. And then moving to the external sites, there are a number of different locations on the space station that are available to US researchers. And not just locations on the US part of the space station, such as the truss, where you can see where you see those red words that say ULF-6, 2011, ULF-5, those are the ELC locations, the Express Logistics Carrier locations. But there are also half of the locations on the Japanese Kiba laboratory belong to the US, and half of the locations on the Columbus External Payloads Facility belong to the US. So there's a lot of capability there. Next chart. And this just gives you a little tighter picture of what those external facilities look like. In this photograph, sticking out from the Kibo back porch, you can see 3 payloads that are sticking out there. They sort of look like Tinker Toys that have been inserted and latched on to that platform. Next chart. And these are just some more diagrams for your reference. Next chart. And one more, please. One more, sorry about that. I put a lot of detail here because those scientists that we're working with that are looking at putting instruments on the ISS have been finding it difficult to find information, so that's one reason why I put a lot of extra detail on that. So I hope you life scientists and shirt sleeve people will forgive those external details. Next chart. And here's an equivalent chart for the Columbus EF showing you the look directions and all of the services on the Columbus sites. Next chart. And let's skip one more. And this gives you a summary of the allowable up mass and volume summary for all of those different external platforms. Since our external scientists have such a menu of sites to choose from, it can be a little bit difficult to figure out what's available and what capabilities there are and do that trade study. And we do have technical experts in the payloads office that can help with some of those trade studies as you investigate whether or not an instrument would be appropriate. But this gives you a place to start. Next chart. And last but not least are the ELCs. The Express Logistics Carriers are attached to the truss.